Hey everybody. A while back I gave a demo to my team on Python decorators and I thought I should make a video about it. So it's not about what decorators are or what they do, but something very specific about them, which is how they are applied and resolved when you decorate your functions and classes. So we'll write a bit of code, and what I'll do is I'll share my screen. So what I have here, basically two terminal windows. On one, we'll be writing some code using the system installed Python version, so the standard Python that you can download. And then on the other window, I have the cPython repo clone from GitHub, which you can do as well. And what we'll do is we'll edit the source code later and then modify the decorator resolution order and see if that works. All right, so even if you have interacted with decorators on a very basic level, you would be able to, I think, find something of interest here. If you have, for example, written unit tests and used the mock.patch decorator, then you have to be, and you have mocked more than one library or function, then you would know that the stacking of the decorators has to be in a very specific order. So it'll become more clear as we go along. All right, so on this terminal, let's just see the system installed version is there, and the version I think is 3.6. Yep. So let's just launch a shell, and so we're going to write two functions, two because we need to stack them on the third. We need to decorate the third one with the first two. So let's just call this function G. Since it's a decorator function, it needs to take in a callable, but for our case, it's not really relevant because we aren't doing anything on that pass argument. So that's G. Now define H, which would be the second decorator, and it also just prints H. And now now let's decorate, G, decorate with G, and then decorate with H, and then define our own function, and it does nothing. So now when I press enter, it should first print H and then print G. So basically execute H and then G. So let's see. Yep, it does that. So that means that by default, the bottommost decorator is resolved first and the top one later. This would make more sense to you if you are like far more mathematically literate than myself, but it intrigued me for a very long time that why is this the case, why it's not top down. So just wanted to figure that out. Another thing, that this way of writing is basically just a fancy way of writing this. So what it does is it assigns to I, which is this function name, the value of calling G on H, which takes an I. So as you can see, this does the exact same thing as this pattern. All right, and so even in official documentation, I think it's called syntactic sugar. All right, and now a more practical demonstration of that stacking. Let's use the mock module from unit test. And oops, I did a typo. All right, and let's just have two modules, and then we can use their functions to do the mocking. All right, and now let's do mock.patch and then sys.version. I think it needs to be a string so that it can be split later, and then time.sleep. So now define our test function, which takes in the first argument called, the naming of the argument, as you might know, is not important, but for the sake of clarity, let's name it mock time, and the second one mock sys. And then assert that mock time is indeed time.sleep, and mock sys is, assert mock sys is sys.version. Now, so this first argument, the way that the mock.patch function would work is that the first argument would relate to the first object being mocked, and the second argument will go to the second one. So this assertion should pass because the first argument would go to the bottommost decorator, and the second argument would go to the decorator above it, and so forth. So if I call my test function, the assertion should pass, and it does. Now let's revert the decorator order. So sorry, not the decorator order, but the assertion order. So sys.version, this is the same. Then the function definition is the same as well. Now assert mock time is actually sys.version, and assert that mock sys is time.sleep, right? And now the assertion should actually fail. and it does, right? So let's move over to the other terminal window. And as you can see, we have the cPython source code here, and let's just go into the directory, and it has lots of folders and stuff. So two things that I've done already is that I have cloned the repo, as you can see, and then I ran the configure script right here, and that yielded a make file, which we will now use to construct a Python binary itself. Okay, so this takes a bit of time, like a few seconds, and hopefully it will compile successfully. Maybe it will fail on some modules, but we are not really concerned about those. We're just doing all the built-in stuff that's available anyway. And we should have the Python binary appear somewhere here. Fingers crossed that it compiles. Okay, all right, it does. So as you can see, some modules fail to compile, but that's not a problem. And we have the Python binary here. Now, if I launch that Python, you can see that it's Python 3.10, which I think isn't released yet. So it's just under QA or something. Now let's mimic the same code that we wrote in this terminal and here, and we should see the exact same behavior because we haven't modified anything. So def g takes in something, prints g, and then def h takes in something, prints h, and now decorating with g, decorating with h, def of I doesn't take anything, doesn't do anything, and it should print h and g. All right, so the same behavior. Should we write the unit test stuff again just to show it? Yep, we should, I think. Unit for test, import mock. The import takes a bit of time because it's locally compiled, so I don't think that caching has been done already. And now import sys, and then what was it, time? And now dot catch sys.version mock dot catch time dot has to be string time dot sleep, and now def of test, and for the just to gain some speed, let's call it arg1 and arg2. And if I assert that arg1 is the bottommost, which is time dot sleep, and assert that arg2 is the topmost, which is sys.version, these assertions should pass, and they do. All right. And now comes an interesting bit. So let's go into the compile.c file, which is responsible for compiling our functions and modules. So let's go to, and it took me a while to figure it out that the Python folder has the compile.c file. So I go there. And now if I look for decos, there is this decos here. All right. This is the compile decorator function. Let's not go into too much depth about it. For one, I don't really know much. And then this is called from the compiler function, and this itself is called from the compiler visit statement, I think. Yep. So this is the code flow: compiler visit statement, compiler function, and then the compiler decorators. So if I go to decos again, so this is responsible for traversing over the decos list and then literally, I think, visiting them. So I'm not sure, I'm not exactly familiar with C, but I think this is the abstract syntax definition language expression. Don't know what that does. So if I just modify the for loop here and start from, so it starts from 0, goes to the end. I'll start from the end and goes again, go backwards. So if I do I equals ASDL sec is now I'm literally just copying decos, and then come to, actually, because we're starting from the end, let's do a -1 so that we stay in the bounds of the array, and keep going until we are greater than equal to 0, and of course then go minus, and we don't need this stuff. So let's look at it again. Looks all right to me. Let's look at the diff. So starting from the end, -1, so that we're inside the array, keep going until we hit 0, and minus. All right, now we need to compile Python binary again because we have changed the source code. So this, the last one was 1614, and let's compile again. If there are errors, it'll just pop up. If there are none, it should compile successfully like it did the last time, and then we'll just launch the binary again. Bear with me for a few more seconds. And what we are going to do then, we're going to write the same pieces of code again and see if the reversal has taken place. So basically, when we write this again, instead of printing H first, the bottom decorator, it should print G first. Oh, and it has compiled successfully. So that's a good sign. The timestamp has changed. So now let's launch this one. Cool. Let's start writing. Def of G takes in something and then prints G, and def of H takes in something, prints H. And now decorating with G, decorating with H, our function name is I, and then we do a pass. So it should first print G and then H. It does. So we have successfully reversed the traversal order. There should never be a need for you to do it ever, I think. But yeah, just to demonstrate why it works this way. And let's do some testing using the unit test. From unit test, import mock. And it takes a few seconds again. And now import sys and time and mock.patch. Sys.version, I think, was our first one. And mock.patch time.sleep was our second one. Now write test. Let's name them properly. Mock time, mock sys, and assert mock time is time.sleep. And so the first argument goes to the first decorator, the bottommost one, assert mock sys is sys.version. Now these assertions should actually fail because we have reversed the order. So actually mock sys will be assigned to the mocked object of time.sleep. Yeah. So let's call this, and the assertions do fail. So the reversal is successful. Now let's fix that. Fix as in like we should assert as is expected in this modified binary. So writing the same bits again, so writing the same function signature. And now assert that mock time is actually, so the first one should go to the first, the topmost one, sys.version, and then assert mock sys is time.sleep. And hopefully it will pass. It does pass. So we have successfully reversed the order. Nothing special there. So the question is, why did we actually have to start from the end and go all the way to the 0th index to have them resolve top down? All right. So there are two answers to that. One is, let's look at the diff again. So one is that the decos list is actually, the decorator list is actually in source order, and the function bytecode is in a stack. So when you put things in source order into a stack, then when you pop them out, they are in the opposite order. So that's reason number one. But it begs the larger question that why everything in Python or around decorators is structured the way it is. So for that, I'll refer you to an email thread between Python's core developers from 2004. So if I actually go to the previous message, Raymond Hattinger, who is a prolific educator himself, I highly recommend looking up his videos. He asked other, I think, authors that please explain why the resolution is inside out instead of top down. So basically, exactly the question that we are trying to address. And then look at the next message. It's interesting how Guido has almost nonchalantly responded to that, saying that this is the usual order function application. F of G on foo means calling F on G, taking in foo. All right, so that's about it. Thank you so much for watching and happy development.